So I'd like to talk about something that we've worked on in the past and a few years ago, and I've been sort of keeping in mind for a while and working on it a little bit at a time when I can find some time outside my other obligations. Let me give you an outline of what I'll talk about. Well, first of all, I'm going to do some shameless self-promotion. I'll talk about Materials Research Collaborative Access Team, Sector 10 at the Advanced Photon Source, which is a facility that I'm responsible for operating. Then I'll talk about this yttrium metal O3 chromophore system, which is a very cool system because of the visual aspect of it, as far as I'm concerned. I'll talk about the long-range structure of yttrium manganese 1 - X indium X O3, and then the local structure of that same material, and then a more recent work that I've been doing for the analogous gallium system. And then finally, a few conclusions. So this is my self-promotion. I run the Materials Research Collaborative Access Team. It specializes in X-ray absorption spectroscopy and does electronic measurements and local structure measurements. Our focus is in situ experiments. Right now, we're a little bit faster than 1 minute, than 2 minutes, probably like 1 minute for a standard XAFS, and we can go faster, quite a bit faster than that for our XANES at the insertion device line, where we can go from 4 kilovolts to about 65 kilovolts, and we can do continuous scanning. That's our standard operating method. We also have a nice Marion 7-element electronically or electrically cooled detector, so we don't have to use liquid nitrogen, and that really works well for dilute samples. We've been getting the electronics up and running, and it's performing quite nicely. We have a microprobe. We can do microdiffraction. We have a high-energy X-ray photoemission system in the back of the hutch, and we've done a lot of remote operations over the last 2 years. The bending magnet line is the data I'll be talking about today was taken the bending magnet line. It works from 4 to 32 kilovolts. It does continuous scanning at about, we could probably do 4 minutes. And we have a silicon drift diode detector for dilute samples and thin films, and we can go quite dilute. So the active membership of the MRCAT is Illinois Tech, the Chemical Sciences and Engineering Division at Argonne, Argonne Biosciences, which does environmental work, the EPA, UOP Honeywell, Des Plaines, Illinois, and BP in Naperville. What we do, and this is just taken from my work, is we've done catalysis studies. We're actually working on this now. We're looking at ethanol oxidation and formic acid. But we have a bunch of different cells. We can help people design cells, and our staff is really good at supporting these kinds of experiments. And of course, we do continuous scanning in all of these. We also do battery work. And this is a couple of examples of recent battery work, which I'm not going to dwell on. They're in the slides. And again, we can do fast scanning. We've been working with Jeff Terry, who spoke earlier this year, I believe, on using the data that we extract here with his machine learning programs. We have the HAXPIS system, and then we have the microfocus stage here with X-ray emission spectroscopy. So the other thing that I wanted to mention is we have a Beamline scientist postdoc position open. I'm not going to say anything more about this because I don't want to spend too much time, but it's going to be in the slides so you can take a look. If you're interested, please contact me. All the information is right here. Okay, so the work I'll be talking about today was done in close collaboration with another speaker from earlier this year, Soham Mukherjee from Uppsala, and his thesis advisor, Didi Sharma from the Indian Institute of Science. And then the work on the gallium samples was done by one of my master's students at Illinois Tech. This is supported obviously by MRCAT, by our synchrotron center. We had some support from the NSF for our collaboration with D.D. Sharma, and then the Dutch Squad Leadership Program, which endows my chair. All right, so the materials I'm going to talk about are based on yttrium indium oxide, which is a white compound, colorless white. And when you dope it, it gives you some beautiful colors. You can see here a doping with iron in the indium site gives you this very strong orange and yellow. You can get green out of co-doping with copper and titanium. You get purple out of doping with manganese, titanium, and zinc. And then the one that I'll be talking about today is this indium and manganese doping. And this structure is a hexagonal structure. It is not a perovskite. And these intense colors have been used. Actually, the manganese version is now in Crayola crayons. And this was discovered first in the 2009 or so, maybe a little bit earlier. And there's this nice paper by Lee and Subramanian from Oregon State University, and a bunch of other people, obviously, that has this whole range and talks about the whole range of colors for this base compound. So it's a hexagonal structure with YO6 octahedra, and they're very flattened octahedra. In fact, sometimes when I look at this structure, this oxygen atom here becomes part of the yttrium polyhedral sphere or coordination sphere, and so it might actually be 7 coordinated rather than 6. It's very close. It depends on the structural twisting that you have. And then you have indium O5 trigonal bipyramids. And so these have a threefold symmetry in the structure. And that's why you get these beautiful colors, is because of the fact that you don't have an octahedral environment for indium. So this material, the one nice thing about the yttrium manganese indium material is that you have a full solid solution range, and you can make it all the way from pure indium to pure manganese, and it maintains the same hexagonal structure. That's not always the case for all the other ones. They're a little bit tougher to make this way, and you can't always make them over the full range. So these are the diffraction patterns from the Smith paper from 2009, and these absorbance data, which show that there's an absorbance in the blue, absorbance everywhere but the blue, and there's a dip here where you get this beautiful bright blue color, and it gets a little darker, gets very dark here, and becomes black by the time you reach manganese. And as they point out here, this is a consistent structure. There's slight changes in lattice parameters. They deviate smoothly, but you have the same structure all the way from x equals 0 to x equals 0.95. We made the same samples, and we just made them by solid state methods, grinding and firing. And these are the samples we made all the way from 0 to 0.95 for x. And as you can see, and so 0 is full manganese, and 0.95 is just a little bit of manganese. This is the one that has the color to it. And you can see the Rietveld refinements here are quite good. So there's really no secondary phase. These are all refining to very good values. And if you plot the lattice parameters, and this is our data now, you see that the C parameter increases as you put indium in. Indium's bigger, so it smoothly gets bigger. It follows a nice linear trend, as does the A and B parameters. They also get larger, but more slowly. And you can see the lattice parameter at the start here for the pure manganese is 11.4, and the A and C parameters are 6.15 or so. So all the samples are single phase. The lattice parameters vary according to Vegard's law. And the real question is how the local indium and manganese environments vary. So when we first started studying these, we took a lot of data on all these samples, and we then started fitting them with what we thought was the standard, solid solution, random mixing of the materials, and we got some answers, and we got fits. But the fact that we presupposed that we had a solid solution that was well mixed gave us a problem, and that when we looked at the XANES. So we started staring at the XANES, and we realized that in fact things were not as they seemed to be from a pure solid solution random mixing perspective. That's what had been done for the DFT calculations. That was what we had done our fits for, and we got reasonable fits. It's just that they didn't make a lot of sense. The parameters weren't coming out very well in the XFs. So we realized that in fact we should look at it in a different way. The isospectic points that you see here in the manganese and in the indium, although they're not quite as developed there, not quite as obvious, but both the manganese and indium show isospectic points. And that sort of tells us that we're looking at something that's not necessarily randomly mixed. So we decided to take a different approach to the fitting. And we decided to fit the endpoints for the manganese and the indium. And so this is the manganese 0.05, indium 0.95, and this is the pure manganese. And you can see there's significant differences. And if we fit these individually, we get different local environments. And I'll detail that a little bit more later. But in the future, I'll be having the blue being the dilute manganese and the black is the pure manganese, sort of following the colors. So what we can see here, just briefly, is that you have, in the pure manganese, you sort of have a symmetric arranged axial direction around the manganese atom. Now remember, since this is pure manganese, all these additional ions here are manganese ions. And the distances in the axial direction are nearly identical. That's the standard structure. And in the equatorial direction, there's, I believe, two, I'll have those a little bit later, two long ones, two short ones, and one slightly longer one. However, when we get to the dilute, now we have a situation where we have, say, one manganese surrounded by indium everywhere. And as we'll see later, the indium surroundings, the distances are much larger, the lattice parameters are larger. The indium occupies a bigger trigonal bipyramid. And so that manganese is sitting and able to move around a little bit. And in fact, you have a lengthening of the axial bond here, and this one is shortened. So you now have an off-center manganese. And that off-center manganese, because of the crystalline electric field, is what produces the blue color. So once we decided that, we decided, well, let's see if we can do some fitting of the XANES only. So we took our endpoint of XANES and we fit all the intermediate diffraction XANES patterns. And in fact, we get extremely good fits. And we can fit every one of them with a simple linear combination of these two endpoints. Now it's 5%, so it's not as dilute as maybe I'd like it to be, but it's still quite close to being, it's 1 in 20 unit cells, which is okay. That's not too bad. And so we were able, I'm showing here the x equals 0.5. You can see it's really quite good fit. I usually don't see this good a fit with XANES, and all of them were basically fit like that. I'm just showing this one as an example. So then we fit the XFs, and we realized that we could get very good fits of the XFs data for the endpoints, the x equals 0 and the x equals 0.95, and you can sort of see This is the magnitude of the chi of r, and here is the real part of chi of r. And you can see over a wide range, we fit it out to 4 angstroms, almost 4 angstroms, so several shells out or longer paths. We get very good fits for these 2 data points. And then we decided, okay, so we have the 2 endpoints. We'll now try to fit all the other spectra as linear combinations of these 2 models, not changing the models at all. So we left these models constant, and we just used them with 1 parameter to fit all the other data sets. And that's what I'll show you next. And as you can see, we get quite good fits all the way. Remember, 0.05 is our one of our endpoints, and 0 is our other endpoint. And for these samples here, at up to, and 0.95 is the other endpoint, of course. So we get very good fits out to about 2 angstroms for just a linear combination of these data sets. And this is the manganese edge, and we did the same thing with the indium edge. So we took 2 endpoints that we had. In this case, it was, we didn't have x equals 0, so we took something as close as possible to full indium. And actually, we did have it. And over here, you can see the results of these fits. And we have the dark blue, or the filled in blue triangles, are the fraction of number 1, which is the blue color, and number 2, which is the black color. And similarly, number 1 of the indium and number 2 of the indium. So as the amount of the dilute manganese environment drops linearly, then of course the amount of the concentrated indium goes up. And so these 2 lie very nicely on lines that match up to each other. That is, the indium and the manganese give you the same results. And this is basically the same result we get from the XANES fitting. So it's all identical. So the next thing we did is we took a look back at the optical properties and tried to understand whether we were seeing something consistent with this idea that what you're getting from the color is really not a change in hue, but just a mixture of less blue material and more black material as you go out in composition, as you change composition. And in fact, if we look back at the optical data, it was from the original paper in 2009, you can see that the centroid of this dip, which is the blue dip, is pretty much constant. It just gets broader and broader as you get to a smaller composition of manganese. We also took Raman data on these samples, and again, over here at x equals 0, which is all manganese, and the x equals 0.95, which is mostly indium, you can see that there's a significant difference in the Raman spectra from the x equals 0 to 0.95. And in the middle, you can see how basically these are just overlapping. So as you go up, you get more and more of the blue and less of the black. And in the middle, you have this broad peak, which is shifting from this value over here, which is about 700 inverse angstroms, over to about 610 or something like that when you get to the chromophore, the blue chromophore. And this is basically just another indication of this mixture of phase-separated manganese, basically. So I can pause here if there are questions.
Very good. We have a question. Sorry, I'm having a little bit issues with my chat. guess my first question for you is you're taking a model of superposition of two phases, two endpoint phases, and do the fit coefficients you get for the linear superposition at the XANES agree with the fraction that you infer for the two-phase mixture from the EXAFS?
Yes, they do. They're basically identical. We just didn't plot them on that figure, but they're identical.
Okay.
We just wanted to confirm it with the EXAFS as well.
All right, very good. Hang on, we've got more messages here. Micah, you have a question?
Yeah, I was just looking at this Raman spectra you have here, and I wasn't familiar with those units, and I was just trying to figure out which vibrations.
Oh,
those are looking at.
That I don't know. Okay, so there, I have to tell you that I'm not an expert. Okay, I'm looking at this qualitatively. This is something we haven't published yet. We're just looking at this in a qualitative way, but I'm going to get to this a little bit later. I'd like to know which vibrations they are, but not being an expert in Raman, I can't tell you that. I'm sorry.
Yeah, I'm not an expert anyway, so don't sweat it.
All right, Xiaofeng, you have a question?
Yes, thank you, Jerry. And nice talk, Carlo. I'm just had a really puzzle question that why in front of XANES that you observe off-center distortion, but in your XRD that you still observe a linear trend?
Well, that's a really good question. I can't give you an exact answer on how big, and this addresses what Matthew's saying as well, was what Matthew's asking. At what point is it going to be necessary to say, well, there's an average structure? My guess is if you heard Shoham's talk, we talked about that before. He talked about a different system where he was looking at how quickly the structure relaxes from the local chemistry to a bulk value. And it's about the third shell, if we talk about shells, about the third distance out or the third near neighbor, you get a structure that relaxes. So my guess is that these domains are probably, and this is just pure speculation because I don't know, my guess is that these domains are probably only a few unit cells in size. And I have some slides that I actually didn't include. And exactly, the correlations have to be there, and XAFS doesn't require it. So if you have uncorrelated displacements, where, for example, it's not ferroelectric or ferromagnetic or something, ferroelectric where everything is off-centered in the same direction, you're going to, it's just going to look like a bigger sigma squared, right? And that's really what's happening here. But my guess from our experiments with the zinc sulfide and the cadmium sulfide is that these structures will relax in a few unit cells. That's my guess. But we didn't really speculate on how big the nano domains can be.
Thank you. Thank you.
And I've seen this before. Many years ago, with high temperature superconductors, we saw these correlations being nano domains of orthorhombic structure that gave you superconductivity, but it looked tetragonal. Same kind of thing.
Okay. Suggestion, Carlo, don't watch the chat at all.
Okay. I will not.
Everyone should make sure they mute their mic. It's just that people following the recording later won't be quite sure what's going on at some points.
All right.
All right, great.
Should I continue?
Seeing no more questions, I think you've addressed the XRD question. I think we should continue.
Okay. So one of my questions, this is something that I've been fooling around with. Again, I'm an experimentalist. I run beam lines and I make samples, or my students make samples these days. I decided to, during the pandemic, to fool around with DFT calculation, so I'd learned something myself. So my question was, can I reproduce the XANES from first principles? The DFT calculations that had been done for the paper in 2018 were done with a random solid solution assumption of a distribution of manganese in indium, for example. And our EXAFS data said that that's probably not the right way to look at it. So what I decided to do was use this program that I happen to have, V2K, to try to get the local geometries and then calculate the XANES. So I started by taking the yttrium manganese O3 unit cell and just relaxing it as a single small unit cell. That's pretty fast. Just to make sure I started from a good place. I did the same with the indium. And so I started with something that at least was converged with the V2K program. Then I took a 2x2x1 indium O3 supercell, and that's what I'm showing here. It doesn't show anything down here because they moved out of the, they moved into the lower cell after the relaxation, and then put a manganese ion in the middle. And so my hope was that this manganese ion would be far enough away from the next manganese ion over that it would be sufficient to give me something reasonable. And I didn't want to make the unit cell so big that it would take forever to do the calculations. So because these are using, typically using periodic boundary conditions, there would be another manganese out here, another manganese up here, and so on. And so I put a single manganese substituent in and I relaxed the system. And so this is what I got. So we start looking at the manganese. You can sort of see this environment is relatively symmetric with pure yttrium manganese O3. There are some slight differences here in these distances, but not large. And that and that's where we start from with the yttrium manganese O3. On the other side, we have the yttrium indium O3, and I tried to make these to scale so that you can see that the arrangement around the indium is also relatively symmetric, but it's bigger. That is, the distance from this oxygen to this oxygen is significantly larger than the distance from this oxygen to this oxygen. When I do the relaxation of doping the manganese in this sea of indium atoms, then I see the following distortions coming in. I get a lengthening of the overall distance between the axial. They're closer to the indium size than the manganese size. That makes sense, of course. That's sort of, there's a big hole there, and the oxygens are sort of tied into the yttrium on either side, and so they'll be farther apart, which makes sense. But what happens then, in addition, is these oxygens get pulled in tighter. So you can sort of imagine that the volume of the polyhedron or the trigonal bipyramid around the manganese is constant. It gets longer, but it gets thinner. Okay, and I haven't calculated the volume yet, but that's something I'd like to do and just get an idea of what's going on. So that's sort of saying that the volume that ion surrounds itself with is sort of constant. And again, this is something I've seen before many years ago when I was looking at Vegard's law and how you best plot it. And then the other thing is you can see that the manganese is now displaced to one of the axial oxygen atoms. So it's closer to the one on top than it is the one on the bottom. And there's a tilt to these oxygen atoms as well. That is, they're not in the same plane or very close to the same plane, or as close to the same plane as they were before in the manganese or in the indium. And these are exactly the kinds of things that we see with the EXAFS. This is very similar to the kind of results that we get in the EXAFS study. So I then took FEF9 and I took the results of these V2K relaxed structures, and I calculated the XANES for the yttrium manganese O3 and the manganese doped into yttrium indium O3. Again, blue being the blue color and the black being the black color. And then I compared them to the data that we had actually obtained from the two endpoints. Now, clearly, this is not infinitely dilute, it's 5%. And so there could be some clustering, who knows. But I was quite encouraged by the fact that some of these features are actually reproduced in this in these spectra and in the calculations. I don't think I'm quite there yet. Again, this sort of speaks to my inexperience or lack of experience with DFT calculations, and this is sort of something I'd like to deepen a little bit more, and maybe I'll have some more time soon to finish this up. But it's very promising. It looks like I might be able to actually get something that's very, very similar. Clearly, there's some problems. The energy shifts aren't quite right. I'm getting a little bit too much here. Maybe I just don't have the right parameters in for the XANES calculations, or perhaps I haven't done the DFT calculations quite right. And so I'm probably going to work with somebody and consult with somebody on that to do it a little bit better, or multiple people. What my ultimate goal is, of course, is that once I have the right structure and I can show that that's what I have with XANES, I know I can take the results of my DFT calculations and then predict the Raman spectrum. And presumably the optical spectra as well, which is what my real goal is to get to the optical spectra and sort of be able to predict this mixture of the two different spectra. So that's where I am with the yttrium manganese indium. I'm happy to answer any other questions here before I move on to the last bit.
Yes, sorry, my mouse pad is behaving badly. And you may want to turn your speaker down a little bit. We're getting echo.
Okay. My volume and my microphone? Yeah.
All right. So first, Micah, you had a comment?
Yeah, I was just going to point out that when you're drawing those structures, you can get the polyhedral volumes out of the drawing program.
Thank you. I will definitely do that.
Very good. Matthew Marcus, you have a question?
Come on, there you go. I was wondering if the disagreement that you're seeing on this slide is, where does it lie? Is it due to the input structure from the V2K, or is it due to FEF9 not being able to be quite accurate? And that could be tested by putting in the known crystal structure, experimental crystal structure of YMnO3.
Yes, and I've done that, and that's pretty close to this. There's not much change in the YMnO3.
Okay, so, and I was also wondering if in the DFT, did you have to start the manganese atom off-center to keep it from getting stuck in the middle?
I have not had to, because there's enough asymmetry in the initial structure that it moves immediately off-center. And part of it is because I don't move the oxygen atoms. So the oxygen atoms are now much further out than they were for the YMnO3. So I just put the manganese in place of the indium naively, and it moved. It took a while, but it moved to the right, to this spot, which is pretty remarkable, actually. I think you're probably right. I should have maybe primed it by moving it a little bit.
Well, it looks like you didn't have to, because I guess the top and the bottom layers are not quite the same, and so and so that primes it for you.
Yeah,
makes for a non-zero force.
Yeah. Other questions?
Yang Ha, you had a comment?
Yeah, very interesting. So your distortion on the manganese side reminds me of the structure of the molybdenum O3, where molybdenum has 6 oxygens around it, and there is a distortion while 2 molybdenum O bonds get extremely short to almost double bonds, while the other 2 molybdenum O bonds get super elongated. And there is explanation on that on the pseudo-Young-Taylor effect. And I wonder if a similar theory can be applied to your system here, where your manganese also has unfilled d electrons, that the electronic structure may lead to this distortion.
I'm sure that adds to it. And in fact, I think manganese is a Young-Taylor ion, I believe. So it does have Young-Taylor effect in an octahedral environment. Clearly, this isn't an octahedral environment, so that it's more complicated because it's a trigonal bipyramid. So there's there's quite a bit different symmetry breaking here already. Yeah. But yes, I wouldn't doubt it.
Thanks.
And then I'll just mention there's a comment from Micah who says that the Muffington approximation is a significant candidate for the disagreements between theory and experiment here.
In that case,
of course,
FTM-NES could be used. Yeah.
Well, I mean, I'm open to suggestions on doing better than this. There is some. Wien2K presumably does XANES calculations. I have not gotten it to work as well as FEF. I'm not satisfied with what you get. Maybe because the energy is a little bit high on this, it may do better on the very low energy edges. Like, for example, the L edge of manganese, it might be better with that. But I was not satisfied with the way Wien2K worked out.
All right, you should continue, please.
Okay, so, well, of course, I got interested. I had a master's student who wanted to work on something. I said, well, why don't you make this purple one? The manganese gallium is very similar, but it's brilliant purple. And so we wanted to see, is the same thing going on here, or is it different? There's nothing to believe that it would have to be the same. And so he tried making the full series of manganese gallium, yttrium manganese gallium oxygen. The problem is it's much harder to make. It's the only one that we know that goes across the entire range, and that there are structures on either end that are identical. The problem is there's a garnet structure that builds up in between. And you can see over here, he was trying, when you're in the very dilute manganese and the high gallium content, we have to heat it for 15 minutes or else we get garnet. You can see right here, this is a big garnet peak. And if you heat it at 850 for 15 minutes, you're not seeing much of the garnet peak. 900 at 10 minutes and quick quenching, it's a little bit better, but the peaks are very broad. It's not well crystallized. And so there are very big issues with making a material with a very low quantity of manganese in this. But he did his best. I mean, he tried to do his best on this. It's just a little bit tricky. We did it by sol gel to try to reduce the amount of time. So we were able to make it up to about 0.5, maybe 0.75. But you can see that the c-axis is not changing here. So I think we've reached a point, and over here is certainly not working well. And you can see that at x equals 0, of course, you get good crystallinity. And all the way up to 0.5, you can still sort of see that it's okay, but it's getting harder and harder to crystallize it well in the time that we have, so that we can anneal it. So there are real problems there. We still haven't worked it all out. However, in general, we're seeing the same kind of phenomenon. So we said, well, this is what we have. let's take measurements and see what we get out of our out of the XANES. And in fact, the XANES still show isospectric points, and that would indicate that we're having the same thing happen in this system. The gallium edge also shows isospectric points. We have not completed any EXAFS analysis on this. We're concerned because of the garnet phase. We really would rather have a much more pure phase to get this done. But it's promising, it's interesting. And now the question is, well, is there a way that I can work on this without having to make the full composition range? Because the other materials have a limited composition range, the other colors. So the EXAFS is here, and again, you can see that there are certain trends that are consistent with the oxygen peak increasing here, this one decreasing the same way with the gallium on the gallium edge. Again, we haven't done a full analysis of this yet. I'd rather have better samples first. And I really have to have some rapid thermal annealing, I think, to do this right. So, that sort of ends the data that I had. I wanted to just have a few observations to finish up. So we do need to do better with the manganese gallium system, and I definitely like to work on the iron system, the one that's yellow and orange. And I suspect that's going to be the same kind of thing, but it's worth trying. If I can do better on the DFT XANES calculations, I might be able to use those calculations as endpoints so that I don't need to have a full range, and I don't need to have the endpoints experimentally to be able to understand what's going on or try to fit the data that I get in EXAFS and XANES. Not clear, but that's my hope, and that's why I'm still interested in working on this. It looks like bimodal environments are general property of this system, of these two systems at least. I expect it's the same for anything that is doped into yttrium indium oxide. My guess is it's probably the same. It's just the crystal electric fields are slightly different, and consequently you get different colors, and the ions are different as well. And the other question I have is whether other chromophores that are made like this have these kinds of strong distortions that are interesting to study and possible to study by EXAFS. And are they uniformly in the system, or is it this kind of situation where you have maybe two environments with under certain conditions? And then, can we draw any general conclusions? And I don't have these slides today, but we've seen this kind of behavior in other systems, as I mentioned before, and we know that these local structural effects dissipate spatially, and so you can see by diffraction that things look uniform, and clearly these global properties, these bulk properties, actually can come from this disproportion. It's not really disproportionation, but this separation, sort of this local phase separation or nanoscale phase separation, which I find very interesting. It happened to be the case for the lanthanum barium cuprate in the high TC materials. So if there are any further questions, that's pretty much all I had for today.
Very, very good. Let me think for a minute while I wait for people to type in final questions. Any ideas about complementary measurements that would let you push these ideas farther, such as HRFT?
That would actually be interesting. I haven't thought about it, but I think the fluorescence HRFT would give me some insight as to what the level, what you know, what the different levels are for the manganese. Absolutely. I should be able to distinguish the different electric fields, right?
What about TEM-based electron diffraction? So you can try and look at very small areas.
That would be interesting. Yeah, also just to see if you can see these domain sizes. Absolutely.
Okay. High energy diffraction. Let's run down the list. Would that give you a better handle on metal distances?
So PDF measurements for perhaps, yeah.
Okay. Matthew, you have a suggestion?
Yeah, I was thinking, depending on what the domain size ends up being, is that perhaps something like resonant soft X-ray scattering. And so,
yeah, especially looking at the L edges, absolutely.
Yeah,
absolutely, yeah.
Yeah, and actually for indium, the L edge is in the tender X-ray range.
Right. Yeah.
But the M edges would be in the soft.
Yeah, those would have to be done as soft. Yeah, it's fairly low. But it could be done with electron diffraction, I imagine, right?
Well, except that you don't get the element specificity.
That's true. Yeah.
Yeah, so like in the iron or in the yttrium, the gallium, was it? The gallium system is so little difference between manganese and gallium that that non-specific techniques might have a problem.
Yeah.
In fact, that could be a problem for your XAFS analysis.
Absolutely. I actually, all those things are interesting ideas, and I'm planning to follow up on them when I have my infinite spare time.
Right. Of course,
it's a non-funded project. This is sort of a fun project for me at this point.
Of course, this is a plug for ALS.
Yes, of course.
All right, I'll ask a last question, which is that you found this unexpected two-phase mixture in this chromophore. Does this suggest paths forward to make other chromophores? Have you learned something here that lets you do rational design of for these purposes?
Yes, I think so. I mean, I think that the first thing you need is you don't want an octahedral environment generally, right? So that's number one. You need to have something that like the trigonal bipyramid is nice because just a little bit of shift will give you a significant symmetry breaking, which will, can lead to these kinds of effects. Yeah, I think there's opportunities to look for structures that have these kinds of motifs and look at substitutions. And it doesn't look like you need to have, the indium manganese is nice because you have the full range, right, of compositions, but you don't need that. With the iron, I think you can only go to 0.2 and still you get the really nice colors. So these are kinds of things that you can easily think about if you just start looking at some structures, right? Look for structures with trigonal bipyramids or maybe maybe tetrahydrals too might do that. But I think the trigonal bipyramids are good because if the idea of the Jan-Teller distortion is important, then you want something that will allow you to get a nice Jan-Teller distortion. And trigonal bipyramid is good for that.